Computers are binary, either 1 or 0, true or false. It is very difficult to represent an analog system, such as sound, using that binary form, those two extremes, either high or low, nothing in between. Analog sound has multiple values in between the highest and the lowest value. It actually has an infinite number of those intermediate values. How to do that with computers? Well, different methods were devised for that, and there's actually the entire area of entire field of study, which is called digital signal processing, the ways of converting analog signal to digital, digital to analog. Entire books were written about that, but let's focus on what's important for our understanding of computer sound. So the initial ways of trying to tackle that problem was to connect a simple speaker such as this one to the main board and be able to send a signal on or off to that speaker. Switching the speaker on produced a clicking or ticking sound. Switching it off again produced a ticking or clicking sound. And if we repeated that on and off state frequently enough, we were able to simulate some kind of sound, a note, a pitch. Let's try and do that. I created a very simple Arduino project, and I'll share the sketches for that in the article. But let's try and turn the speaker on and off frequently, but not frequently enough to create sound yet. Let's do it every half a second, so we will have the frequency of 2 Hertz, 2 times a second, on, off. That's 2 Hertz. Let's connect the speaker, the Arduino, sorry. And now we hear the on and off switches of the speaker. Of course, this is not frequent enough to create the impression of sound, so let's increase the frequency to 440 Hertz, which represents the note A. And let's freeze the oscilloscope here, and what you see here is 2 states, high and low, and no values in between. So you see there's no slope similar to sine wave, either decreasing or climbing. It's just up or down, and the switch between them is momentary. It's infinitely small, at least in theory. So this kind of wave is called a square wave, and the method of modulating and creating sound with this single square wave is called pulse width modulation. And that pulse width modulation method was used in PC speaker, but not only in PC speakers. It was also used in other computers of that era, of the early 80s. So it was used in ZX Spectrum 48K. It was used in the Apple II computer, which is behind me. It was used in multiple other computers and devices, and actually that square wave is still used to send alert sounds or notification sounds in multiple devices, including household devices. Let's see how to use it in practice. So in practice, what you have to do is to simulate a tune. You would have to just play those sounds in sequence of sounds of varying pitch and varying length. I simulated that effect again using Arduino, and and an old Polish melody for which I typed in the values of notes. Let's see how that works. So that's my tune. A disclaimer in the code that I shared in the article and under this video. I used a very crude method of modulating the width of the wave. I actually froze my oscilloscope. Let us play the melody in the background again, and to see how frequency of the wave changes. But there are built-in Arduino methods which do that in a much more efficient way without locking the main processor, and I can share them in the video under the video as well. But let's get back to the point. So what you see here, if I play that melody again, you see that I'm modulating the frequency of sound, but the ratio between how long the signal stays in the high level and how long it stays in the lower level remains the same. It is around 50% of time. Let's freeze the signal. 50% time the signal is off, 50% on, 50% is off. The ratio of how long it stays high and how long it stays low is called duty cycle, and in this case it's 50% duty cycle. 50% of the time the line is the signal is on or in high state. Let's try another trick. Let's try and play a few arpeggios. Arpeggios back in those days were used very frequently to simulate chords. Remember, we have one speaker and one channel only on and off, so we can't play several notes of a chord together at the same time. But the arpeggio effect, meaning frequently playing the same notes one after another in very short sequence, actually simulates that effect of a chord in our human ear. And let's do that again using our Arduino. I played a few simple chords here using that method. That sound should already start reminding you about the feel of old computer games, because that's how very frequently chords were simulated in computer games using arpeggios. One note played very quickly after another. And one more method. Look, in all the experiments that we ran so far, we retained that 50% ratio, 50% duty cycle. But that duty cycle could also have been modulated, and early game programmers used that method a lot to simulate certain attributes of the sound. In particular, the sound was different when the duty cycle was around 50%, and it was slightly different when it was at very low, like 1 to 10%, or very high, 70, 80, 90%. So what I did here is I created another Arduino project, another Arduino sketch, which allows me to modulate the frequency in a very crude and also in another fine way using potentiometers. And there's another potentiometer which enables me to modulate the width of the high state. So let's first increase the frequency. So we're starting from very low frequency, which actually doesn't remind sound at all. It's not like a single note, it's like just frequent ticking. But let's increase that using the coarse knob. Up to maybe here. And now let's use the fine knob to increase it further. I'm gonna share the code for that in the article and in the description of the video. But I'm using the analog signal to modulate the certain parameters of the square wave. But the square wave still remains at roughly 50% of duty cycle. We're only increasing frequency, and now let's modulate the duty cycle itself. So we're going from 50% to lower or higher, and look what's happening. You hear the frequency remains the same, so the pitch remains the same, but the color of the sound, sort of its timbre, changes. It goes from like a full-bodied sound to something very flat, shallow, or noise-like, tinny effect. Let's modulate frequency and again, and modulate duty cycle. So that effect was used a lot by early game programmers. They actually used more than that, not only modulating the duty cycle, but they also in a smart way modulated the high and low states in such a way that the speaker wouldn't actually fully go out or fully go back in. So there's a delay of like a very small amount of time, I think 60 microseconds, when the membrane goes out fully and goes back fully. So they changed the signal even before the membrane fully went out, which created even more sound effects. And we're going to explore those effects later when we look at specific platforms. But for now, let's just very quickly see the examples of how the 1-bit sound production was used in 2 of our platforms, or maybe even 3, because I also have a non-computer platform. It's more of a calculator. It's a Hewlett-Packard 28S scientific calculator, which actually has a beep command as well, which works the very same way, using pulse width modulation and a square wave. So let's try and hear the sound that it produces. Let's enter a command 440, meaning 440 hertz, space 3 means 3 seconds, and space the command beep. Enter. I hope it's gonna be heard because it's very faint. That was the sound produced by the calculator. It used the very same pulse width modulation method to arrive at certain sound pitches, note values. We also have the ZX Spectrum 48K here, which actually had the beep command built into its basic programming language. And I remember programming melodies on my own with that. It was so great to be able to program computer to actually play a tune. Let's play one note here just to compare the sound. I'm going to display the commands here. You're probably not can't see them from there, but I'm gonna do a close-up later. So let's type beep 3 means 3 seconds, comma 0. 0 means the note C, and let's play it. And one more, maybe a higher note, beep, again 3 seconds, comma 10 this time. So that's our ZX Spectrum 48K. And there behind me is Apple IIe, which has the very same basic speaker as our Arduino or our other computers. By the way, it's called PC speaker, but that method was used across many home computers back then. The same 1-bit speaker and the same creative ways that programmers tried to overcome its limitations. So I loaded an Oregon Trail the Oregon Trail game there, which which was an immensely popular game for the Apple II 8-bit computers, and it already started playing. Let me just unmute it on my mixer. So again, a melody which is being played by creative use of square wave, changing its frequency and how long it's being played, and this way simulating notes. By the way, I had to actually connect the wires of the speaker within that Apple IIe directly to my mixer in order to be able to play this music so that we can all hear it. So you see several devices using the same method. The successors of these devices later were using more advanced computer chips. So, for example, the ZX Spectrum at certain point was succeeded by ZX Spectrum 128K. This is one of the successors, a bit later one, ZX Spectrum Plus 2, but these were already equipped with a more advanced chip. This one is equipped with an AY chip shared by even more Amstrad owned home computers. We're gonna look into AY chip later, but it enabled some polyphony and some sound synthesis. Another one for the Apple IIe, which is behind me, one of the successors, actually the last successor I think, was Apple IIgs, which I have here, which was equipped with a polyphony synthesizer chip made by Ensoniq. Ensoniq is the company that was at certain point acquired by Creative Labs for its excellent chips, and we're going to look into that Apple IIgs Ensoniq chip in detail later as well. And obviously we're going to look at the successors of the actual IBM PC speaker, which is to say that we're going to look into all the multiple sound cards that were produced for PC compatibles. Before we do that though, we will look into how creative were game developers in overcoming the 1-bit limitation. So we're going to look at the examples of some excellent games and audio software for those 1-bit PC, 1-bit speaker machines for ZX Spectrum 48K, for Apple II, and for the IBM compatible equipped only with the PC speaker. There were many ways that the programmers overcame those limitations, and they created some amazing work in that confined space of a 1-bit PC speaker. Let's look at them in our next video.
Bye.